What is the principle of superposition, and how can you use it to make circuit analysis a little bit easier for yourself? Find out right now.
Hi, I'm Dr. Bob. There are no lectures here. I just solve problems, homework problems to help you understand how to do them. Electrical engineering at your service.
Oh, I got some crazy, I wonder if this is ever going to catch up. Alright, and that's our first one. Now, when we do this in Mathcad, we're going to have to change this to a 20. And you can put the volts in or not, depending on whether or not you want to mess with units in Mathcad. The second one we're going to do around, so well, this is around VA. Alright, so around VB, we have our second formula. It's going to be VB minus VA divided by R1 plus VB minus VD over R3 plus VB. Now get this. This used to be VC, and now it's a 0. So that simplifies that, divided by R2. And that's all equal to 0 as well. You know, zeros. And then the third node we're going to go around is VD. And for this one, we have VD. Now this time, instead of going, we're going from here to here, so we're going to add 20 volts plus 20 volts minus VA divided by R4 plus, the next one is going to be VD minus VB divided by R3 plus VD minus, of course, 0, that's what we have over here, divided by R5. That's all equal to 0. And then this one we're going to take note that VC is going to be equal to 0. And so we should be able to get that in our net list. So let's take all of these formulas right here, and remember that the V delta that we have is going to have to, in Mathcad won't be able to understand what a V delta is. We're going to have to tell it that V delta is VB minus VD. And then, of course, it already knows that VC is equal to 0. We're going to take VC out of here because you don't see VC anywhere. This right here would be VC, but it's actually ground now. So let's see what happens in our Mathcad. So we did it in Mathcad. Here's our formula, and let's get our pen back. All right. Here's our 1.5 V delta right here. VA minus VB, VA minus VD minus 20 over R4, and then VB minus VA over R1, and so on and so forth. So we have all our values in here. VD minus VA plus 20 over R4, VD minus VB over R3 plus VD over R5, and all that's equal to 0. Now, in order to get this little equal sign right there, you can't just use an ordinary equals. You have to do, I think it's a control period. Control period in order to get this equal sign right here. And then you specify what this formula is going to be equal to. These are pretty standard things. And of course we get the answers VA, VB, and VD. And once we get those, then we get our values. We take those and we unplug them. Here's VA2. Now notice I've gone not VA1 anymore, it's VA2 because this is the second half of our problem. Here's VA2, VB2, VD2, and we get values for these. VA2 is, VA2 is minus 13.721, VB2 minus 11.628, VD2 is 12.791. let's see, when we did this in SPICE, what happens? Here's our net list. Of course, here's our net list in SPICE. And here are the values. We have VA2, and here's the missing power supply over here. V2 is missing. The VA is minus 13.721. VB is minus 11.628 if you round that up, and VD2 is minus 12.791, also rounding that up. So it looks like SPICE has correctly agreed with us with our calculations, and now we have formulas. Now we have some solutions to the second half of this problem. So it agrees with this. What's our next step? Put them all together. Alright, so what we've done, we've run this in SPICE, we run the whole program here. And once we run the whole program, again here we have a net list from SPICE, and this includes both power supplies this time, the 20 volts and the 25 volts. This one's 20 volts and this one is 25 minus 25 almost. And here's our reference. Remember, there's no current going through here. Right? It's just a reference. It's just a place where we're calling this equal to 0. Everything else is relative because all these power supplies are built into the circuit relative to the other power supplies in the circuit. Then getting used to this pin, VA1 plus VA2, and we get a total. When we add these two up, we get minus 6.287. VB is equal to VB1 plus VB2, and then VB comes out to minus 10.05. VD, VD1 plus VD2, that comes out to minus 10.341. Now, does that match up with what we believe that SPICE should be getting? When we ran this, the operating point was a DC operating point. We wanted to know if these numbers were going to come out right. Okay, so we got minus 10.341, if you get that. VB is equal to minus 10.05, and then minus 6.287 for VA. And that matches up what we get when we run SPICE program, which in this case is LT SPICE. The last thing we're going to look at is the current of G1. We never actually talked about what that value is, but as you can see, there's a current IG1 is 0.436 amps, or 436 milliamps, which is supposed to be 1.5 times the value of VB minus VD. So if we take VD and we subtract from it VD, we get minus 10.05 minus negative 10.341. We get a positive 0.29 volts. And we multiply that by 1.5, and now when we do the calculation in Mathcad, we're getting a few more decimal places that you're just not seeing here. The numbers you see here might not be perfect, but 1.5 by 0.291 comes to 0.436, and what you see here is 0.436, which is the current that we calculate to be correct. And that probably rounds out this problem. I'm Dr. Bob.
Thanks for watching my program. If you like my videos, be sure and subscribe to my YouTube channel. And for an organized listing of my YouTube videos, go to my website, www.wherearemyplacebos.com, and click on videos. Have a great day.